All right. Seems everyone's in by now, so let's get started. Today's topic is leakage tests and specifically uncertainty leakage tests. We have made this presentation to show a typical example which is being exercised in many of the tests. Of course, leakage is a very wide topic. There is not one single way the leakage is tested and measured. So there is not a single way how to calculate an uncertainty. So what I'll be showing today is one pretty typical and very frequent example. First, let's speak a little bit about what is actually leakage. So the leakage is an escape of a liquid or gas from some object, from a technical system, when the gas or liquid escapes, it escapes from certain volume over a time. And of course, the escape is very much dependent on a pressure, or rather a pressure difference between the inside and outside of that object. I've made very approximate example on a ball. Let's say we have a football ball of 22 centimeters in diameter, and it's pressurized to 1.9 bars. And that is to say, in an absolute value. This is not a relative pressure to the atmosphere. This is an absolute value. And let's say such a ball is flat in 1 month. So how to deal with that? We have the volume. Should be using that pen now. We have the volume, which is about 5.6 liters. The pressure difference between the full ball and a flat ball is the difference between what it was in the beginning and a standard atmosphere, which is about 900 millibars, the difference. And one month is about 2.6 times 10 to the power of 6 seconds. So if we put that all together, pair this expression, which is an expression for leakage, we'll get that the ball had to have about 1.9 to times 10 to minus 6, and now the units, millibars times liters per second. Sorry. It's rather strange units. It is not units of flow, which is volume over time. There is also that pressure component in leakage. So leakage is not just a flow. And one important note, the leakage depends on the temperature, and that's for various reasons. And two main reasons is the viscosity of the liquid or gas which is leaking, and the second is a geometrical change of the leaking crack or orifice or whatever it is. So be aware that the units are rather strange. And it becomes stranger, mainly because of the temperature. Because based on the temperature, we recognize three categories of units. That's the operating units in the temperature we actually have. Then standard units, that's at 20 degrees of Celsius. That's the temperature in which most of the tests are carried out. And the normal units, which is at 0 degrees Celsius. That's like the official normal. And quite often we see cubic centimeters per minute, and it's being very often it's being written in this way, rather than cm cubed, cm to the power of 3. We see that cc abbreviation, cubic centimeters per minute, and it does not have that pressure component, as you can see. If it does not have that, we always consider that to be the difference to an absolute vacuum. Otherwise, the difference to the standard atmosphere, which is 1013.25 millibars. So if we assume that to be missing in that cubic centimeters per minute, we can make the conversion. So 1 cubic centimeters per minute is 0.017 millibar liters per second. And then it is also possible to make the conversion on temperatures, which is done by a quotient. That's the ratio of thermodynamic temperatures, either the operating and the normal, or operating and the standard, so you can recalculate that. I would caution here, this conversion based just on temperature only deals with the viscosity of the liquid or gas which is escaping, which is leaking, and not the geometrical difference in the measured object. And that's exactly the reason why this is being done, because we assume that the object should have some operating temperature. If it is in car, it's probably not the 20 degrees Celsius or the 0 degrees Celsius. It's its own operating temperature with its own geometry. So converting just for the viscosity is actually all right. And now the example. As I've said, there are several usual ways of measuring leakage. And the most frequent one is actually measuring the flow, measuring the escape of the liquid or gas, mostly gas actually. And this is for quite big leakages. This is for leakages of around approximately 10 cubic centimeters per minute. And compared to the ball example, it's a lot. It's many times more. So it's really for objects that need to be somewhat tight, but not really. In objects that really need to preserve the pressure, like the ball or a tire or system like that, we usually use different measuring techniques, and quite often it's a test with helium. So we pressurize the object with the helium, and then we don't measure the flow, but we detect the presence of the gas, of the helium. It's called a sniffing test. There is a probe with which we sniff around that object and detect the particles of helium. And one more point, we can also do it vice versa. There needs to be a pressure difference, but it can be the object can be either pressurized or vacuumed. Which way we'll choose very much depend on what is technically possible and what are the actual operating conditions. And we'll no longer speak about the measurement itself, although it's very interesting topic, but we'll speak about the uncertainties, just about the uncertainties. So if we have a measuring machine like this in a production line, it is pretty easy to make type 2 study or to make repeatability, because we have the objects, we have the operators, we can measure the parts repeatably and see what that component of the measuring process is. But what we are lacking is the reference to the master value. Like if we measure 9.8 cubic centimeters per minute, is it really 9.8? Is that component of the measuring machine precise in the sense that it really measures on the scale that we with the correct units, with the units it displays, or is it just repeatable? And this is quite often done with leak masters. It's these little objects that can be plugged on the hoses around that machine and measure one by one the sensors of the leakage. And these leak masters are calibrated. They should be able to preserve that leak, and they are typically in these tens of cubic centimeters per minute. They usually go up to 100, and in special cases they can be manufactured with much smaller orifices starting at approximately 0.1 cubic centimeters per minute. So if your leak should be smaller than that, smaller than 0.1 cubic centimeter per minute, then this technique is no longer practically possible, or it becomes really expensive and not very useful. And these masters, as I've said, these are calibrated, so they come with a calibration report. So how to connect this into the measurement system uncertainty of our leakage test device. And I will show that example in Yarvin. So here we are. We have two measuring devices. One of them is the probe, it is the master, and the second is the measuring machine. And we need to connect them. So we'll treat them one by one, and we'll send the resulting information from the master, from the first one, to the leakage test. So what do we know about the master? It measures one quantity, which is the leakage. and it's being measured in the lab compared to some other master. So on the calibration report, you will find what is the size, what is the dimension of that master, and it will be 10 cubic centimeters per minute in our case. That's what the laboratory device has on itself. It has some resolution, which is not really important because it's mostly negligible. And it has the values which have been measured on that reference value, and the values are measured on that leakage master. And our leakage master, I'm afraid I have not mentioned that yet, is calibrated for 10 cc per minute. That's the reason why we measure it at 10 cc per minute. The calibration report also carries the information on what is the uncertainty of the reference value. Every calibration report should have that. And in our case, it's 0.036 cubic centimeters per minute at 95%, which means the coverage factor is 2. And here are the measured values. It is 10 of them. And if we have that, we can calculate the uncertainties of the measuring system. And the measuring system in our case is the calibration master. So we have the calibration error as a type B uncertainty. The resolution is not used because it's really small, negligible, much smaller than the repeatability we see in the experiments. That's the reason why we don't use it. And we have the bias. Now let's see the detail. Let's see the graphic. There is a trend. This is quite usual to see a trend in the leakage testing. And now the question is if we should be compensating for this trend or not. I would suggest to always go with the more conservative case, which in this example is to compensate for the trend. And the reason is that the master value is actually quite high, higher than the starting point of the master measurement. So if I don't compensate for the trend, the variation, which is the uncertainty of the variation on reference, increases, but the bias increases. Sorry, yes, the bias decreases. Sorry, the variation increases, the bias decreases. But putting these two together will yield a smaller measurement system uncertainty compared to the case when I would compensate the trend. The measurement system uncertainty increases. So I would choose to use this bigger value just for the sake of being conservative. And when I have that, I will continue on with my actual measuring device to see what is the repeatability. So again, I have the leakage in cc per minute. I have the master. And now, what is the master? It can be either what is written on that calibration master with a high uncertainty or I can reduce some components of the uncertainty by putting an average value in here. And this is actually this is the average value from the previous experiment, from the calibration report. And I go next. I will now add the B-type uncertainties. And the very B-type uncertainty I am looking for is the master calibration. And this is the value I have from the previous study. It's this value. It is a little UMS. It's the standard uncertainty. So the coverage factor is 1. If I would be using this capital UMS, I would write there this value and the coverage factor would be 2, yielding the same result in the end. And I would do the standard type 1 study, the repeatability study on a master. I only have 1 master, so we still don't have the linearity, but that's quite usual. In this case, this is data taken from a real life example, and there have been 50 of them. And I will end up with the resulting uncertainty. And in this case, I can actually put in the specification limits. And that is the difference for between the first case and the second case. In this second case, this is the actual measuring device. It has its specification limits. So it's possible to evaluate not just the uncertainty, but also the indices, the non-dimensional indices that are related to the specification limits. Quite often, the lower limit is initial limit at 0, and we only care about the upper limit. The lower limit is natural. It is very unusual to have a lower limit above 0. That would actually mean that we require some leakage to be there. It's possible, but it's not very, very usual. So in this case, the leakage, the UMS, the uncertainty, expanded uncertainty of the measurement system being 0.56 cubic centimeters per minute, is adequate to the tolerance that we want to have, which is about 10, which is exactly 10 cc per minute. So the QMS is at 11%, which is good enough. With the calibration uncertainty being incorporated here. So this is what comes in with the calibration master. Having the calibration master here is actually what we want to have when we do the repeatability on the actual production unit. Looking at this graphic, you can see there is also a trend, downward trend. In this case, again, this is quite usual to be seen in leakage examples. We can have a discussion on whether do we want to include or not. Again, if we pass with the more conservative case, then I would suggest to do that. All right, so this is it. This is what I wanted to show you today. I will recap it. So what we want to have is the measurement system uncertainty of the whole system. And the component which is missing is the uncertainty of the calibration master, or the leakage master, that we have to test the repeatability on a reference. And we can do the repeatability, but we still don't know if the measuring device is biased. And to find that out, we use that orifice, we use that leakage master, but we need to know what is its uncertainty to plug it in. And one of the good ways to find that out is to look in the calibration report of that master. And the calibration report has quite few useful information. And these information are mostly two. The first is the uncertainty of the calibration device which was used to check that master. And it is this. So we go in that chain of calibration back and back, and the calibration report has the measured values, which is a repeatability experiment itself. And this repeatability experiment contributes the repeatability and the bias. So having the calibration value and having the value which is actually measured on that standard gives the bias, gives the relation to the precise value which we want to have. Of course, it's burdened with the repeatability. That's the reason why it's there. We get the overall measurement system uncertainty. We plug it into the second one, into the actual production unit, and we land with what we want to have. And what would we do next? We would do the standard type 2 study, which will land us exactly at measurement process uncertainty. This trick can be used in not just in leakage, but in many cases where we have some master and we relate the exact value to that master, not only in absolute measurements, but also in relative measurements. All right, I see there are no questions today. So I will thank you very much for attending this seminar, and I'm looking forward to seeing you next time.
Diribet, we are Diribet. Diribet, we are Diribet. Diribet, we are Diribet. We are Diribet.